Hello, this video includes information on the second and third laws of thermodynamics. Hello, this video includes information on the second and third laws of thermodynamics and Gibbs free energy.
When we talk about changes in entropy, we're actually talking about different things that we need to consider altogether. We're going to be talking about the entropy of the system, which is what we're actually studying, and the entropy of the surroundings, which is essentially everything else. And the entropy of the universe, the total disorder in the universe, equals the sum of the entropy of the system plus the entropy of the surroundings. Now, a process is spontaneous if the entropy in the universe is increasing, if the entropy in the universe is positive. So if the entropy of the universe is negative, if the overall disorder in the system, in the universe, in everything, is going down, the process is non-spontaneous. That doesn't happen. Okay, the universe overall is increasing its entropy. And if the entropy change for the universe equals 0, that means the system that we're studying is at equilibrium. So you can spontaneously decrease the entropy of a system, like freezing something, if and only if you also deal with an increase in entropy for the surroundings. And the increase in entropy for the surroundings has to be greater than the decrease in entropy of the system. In other words, if this value is negative, this value not only has to be positive, but has to be positive and bigger than this number so that the overall entropy change for the universe remains positive. So let's look at kind of some scenarios for a second. Okay, let's say that we have our system here. Okay, and this is our surroundings here. We always kind of have to identify what our system is versus everything else. And in our first scenario, our system is at a lower temperature, and we have energy being transferred from the system to the surroundings. Okay, well, if we look at the system first, the system's losing energy. And our temperature is always going to be positive because it's always going to be in terms of Kelvin. And Kelvin is an absolute temperature scale. So this value for the entropy change for the system is negative. Okay, the system is losing energy. The particles are going to be more ordered in the system. If we were to look at the surroundings, well, in this scenario, the surroundings are gaining energy. So the entropy change for the surroundings is positive. Now, the system's entropy is going to be changing at a much greater magnitude than the surroundings are. So the overall entropy change for the universe would be negative, and that's not possible. Well, energy isn't going to flow from low to high. That makes sense that our delta S value is a negative value, is less than 0. So now let's look at the next scenario. So now we've got our system here. We've got our surroundings here. The surroundings are at a higher temperature than our system, so hotter, colder. And this time we want to study energy being transferred from the surroundings into the system. So that means that the system is gaining energy. Q is positive, which means the amount of energy or the entropy change for the system is positive. Well, the surroundings are losing energy, so Q is negative. Our entropy change is going to be negative, but again, because the system is so much smaller than the surroundings, this is much less significant a change. So our system is positive. Our surroundings are negative. The positive supersedes that negative value. So in this case, the entropy change for the universe overall is positive. Well, energy flowing from high to low makes sense that it's going to be an increasing entropy value. Now, this third value, we have our system here, and we have our surroundings here. And this time, the system and the surroundings are at the same temperature. Energy being transferred from the system to the surroundings. So the system would have a negative Q. The surroundings would have a positive Q, but the temperatures are the same. And if the temperatures are the same, this value is equal and opposite to this value. And our delta S for the overall universe is 0. We're actually at equilibrium. Energy isn't going to flow from the system to the surroundings. The only scenario out of these three scenarios that's actually going to be spontaneous would be this middle scenario where energy Q is being transferred from the hot universe into the cooler system. Let's ask a question, and we'll do a little bit of math to kind of show it. Okay. Why does water freeze below 0 degrees, but it doesn't freeze above 0 degrees? If we were to look at freezing, okay, we're going from a liquid to a solid. So the randomness or the disorder or the entropy for the system, the water, is going down. So delta S for the system is going to be less than 0. It's going to be a negative value. Now, if we talk about going from a liquid to a solid, the system is losing energy to the surroundings. That means that freezing is an exothermic process. So the surroundings are going to be gaining energy. Energy is going to be flowing from the system to the surroundings, which means that the particles in the surroundings are going to be at a higher temperature, which means they're going to be at a higher entropy, which means that entropy change for the surroundings is going to be a positive value. Now, if we were to look at the overall energy in the universe relative to this change, the delta S for the system is the entropy change when we have a liquid going to a solid. And the delta S for the surroundings can be calculated by taking Q divided by T. Now, when we talk about entropy, entropy is in the term of joules per Kelvin. So that means that if we were to increase the temperature, that's going to decrease the entropy. They're opposites. So an increase in entropy of the surroundings is inversely proportional to its temperature. So what does that mean? If we're at a lower temperature, the surroundings are going to be at a higher entropy. So here's our system here. Okay, it's a negative entropy because we're going from a liquid to a solid. Here's our surroundings here. The overall universe is the sum of these two values. And at a low enough temperature, the surroundings will have a larger entropy change than the system will. That'll leave us with a positive entropy change for the universe. That means this process is spontaneous. So water will spontaneously freeze below 0 degrees Celsius because at lower temperatures, the entropy of the surroundings is greater than the entropy change for the system. But if we're at a higher temperature, if we're above 0 degrees Celsius, a higher temperature means a lower entropy for the surroundings. So our entropy change for our surroundings will be less than our entropy change for our system. And the sum of these values will give us a negative delta S for the universe. A negative delta S for the universe means the process isn't spontaneous. So at higher temperatures, the entropy change for the surroundings is not enough to negate the entropy change for the system to make the overall entropy change for the universe a positive value. So in other words, water does not freeze spontaneously above 0 degrees Celsius. So let's do a quick calculation now. Okay, if we look at solid water, ice, and we change it to liquid water, so we're melting water, the entropy change is 22.1 joules per Kelvin. Now, this is a positive number, and that makes sense because liquid water, the particles in liquid water are more random, less ordered than the water molecules in the solid state in ice. So it makes sense that this number is positive. So 22.1 joules per Kelvin is the entropy change when we melt water. Okay, it requires the surroundings to transfer 6.00 kilojoules of heat into the system. So we have to absorb energy in order for this melting to take place. Is the process spontaneous at -10 degrees? And is the process spontaneous at +10 degrees? So let's mathematically calculate that. So here's our equation. Okay, so let's look at -10 degrees first. Delta S for the universe, which is positive for spontaneous and negative for non-spontaneous, equals the entropy change for the system plus the entropy change for the surroundings, which can be calculated by taking the heat and dividing it by the temperature. So it gives us the entropy change for the system, the 22.1 joules per Kelvin. It gives us the energy that has to be transferred from the surroundings to the system. And it gives us the temperature. -10 degrees Celsius is 263 Kelvin. Now, notice the sign on Q. It's a negative value because the surroundings are losing energy to the system. So the surroundings are losing this much energy to the system at this temperature. Collectively, that gives us the entropy change for the surroundings. So when we plug this into the calculator, we're going to get -7 or 0.714 joules per Kelvin. That means that the entropy change for the surroundings is not enough to supersede the energy change of the system, so it's not spontaneous. We're not at a high enough temperature. What I want you to do is calculate delta S for the universe at +10 degrees Celsius. and see what you get for that delta S for the universe and decide whether water can spontaneously melt at 10 degrees Celsius. Okay, so we're still using that 22.1 for the delta S of the system. Okay, that's the entropy change when solid water changes to liquid water. We want to find out what the entropy change for the surroundings is. Notice that the Q value is the same, but now the temperature is 283 Kelvin. Yeah, I agree. It's a positive number this time, 0.899 joules per Kelvin. So that means the process is spontaneous at a higher temperature. So all this does is it just quantifies the graph we were looking at before. So if we're at a lower temperature, the entropy change for the surroundings is not enough to cancel out the system, but if we're at a higher temperature, it is. So we get a positive value, it's spontaneous, as opposed to at a lower temperature, it's a negative value, so it's not spontaneous. All right, so we're going to look at one more question, I think, and then we'll take a quick break. So when we talk about Q, we know that Q means heat or energy transfer. So Q for the surroundings equals negative Q for the system. In other words, if the system is losing energy, the surroundings are gaining that energy. And Q for the system is also known as our enthalpy change, as long as we're at a constant pressure. We know that delta S for the surroundings is calculated by taking the energy change for the surroundings and dividing it by the temperature. We can just do a little bit of substituting. For Q for the surroundings, we could substitute in negative Q for the system. And for Q of the system, we could substitute in delta H. So delta S for the surroundings equals negative delta H divided by T. So the entropy change for the surroundings will equal the negative enthalpy change for the system divided by the temperature of that system. So let's look at an example. Let's say that we have this reaction here. We're told that delta H equals negative 125 kilojoules. The negative means that this process is exothermic. We want to calculate delta S for the surroundings at 25 degrees Celsius. So this system is giving off energy to the surroundings. How is that going to affect the entropy of the surroundings? So negative delta H over T is the equation we want to use. Now, if delta H is negative 125, negative 125 gives us positive 125. So 125 divided by 298. Again, we want the temperature in Kelvin, so we're just adding 273 to 25. So that gives us 0.491 or 491 joules per Kelvin. This is a positive delta S value for the surroundings, and that makes sense because the system, which is this reaction, is giving off energy because it's exothermic. So the energy is flowing from the system to the surroundings, which means the particles in the surroundings have more energy after this reaction, which means the particles in the surroundings are going to have a higher entropy, a positive delta S value. Okay, so let's do another problem.
Okay, see if we can follow what we did before. So we want to calculate the delta S for the surroundings, the entropy change for the surroundings, when we look at this reaction here. Okay, same kind of problem, except that delta H this time is a positive value. That means this reaction is endothermic, which means the system, which is this reaction, is absorbing energy from the surroundings. So the surroundings are losing energy this time. So calculate your delta S for the surroundings for this reaction. This system is endothermic, okay, a positive delta H value, which means that our surroundings are losing energy. So negative 778 kilojoules divided by 298 Kelvin. And again, we want that in terms of our absolute temperature scale. So we're just adding 273 to 25. So we get negative 2.61 or negative 2,610 joules per Kelvin. Again, the important thing is this negative sign, because if our entropy for our surroundings is negative, it means that the particles in the surroundings are becoming less disordered, or the entropy is going down. And that makes sense because the particles in the surroundings are losing energy when we look at an endothermic process. So when we talk about entropy, okay, by definition, the entropy of a perfect crystalline solid at 0 Kelvin is 0. What does that mean? Okay, well, it means that if we're at 0 Kelvin, there's only one way for the particles in that perfect crystal to be arranged, because the particles essentially have no energy. They're not moving around anywhere. They can only be in one place. So if we were to plug that into our equation, the natural log of 1 is 0. So the entropy is 0. Entropy values for everything else is measured against the absolute 0 of entropy. As the temperature increases, the entropy increases. And we can use these values to do calorimetric measurements. So when we talk about our entropy values, we're going to be looking at values at 0 Kelvin to 298 Kelvin at 1 ATM. And we're going to be dealing with what's called the standard entropy changes for these substances. So if we were to look, it's just on a table. Let's kind of just look at some of these numbers. You would never memorize them. You just have to know what to do with them. But let's take a look at some of them. Like if we were to look at, let's say here, we've got gaseous water versus liquid water. Okay, well, gaseous water has a higher entropy value than liquid water. That makes sense. If we were to look at C2H5OH and compare it to CH3OH, okay, C2H5OH is a more complex molecule. It's going to have a higher entropy value than CH3OH would be, just to give us some general ideas about what those numbers are. So what are we going to use that for? We can calculate the entropy change for a reaction.
And we do that by taking the total entropy change for the products and subtract the total entropy change for the reactants. Now, the V stands for the stoichiometric coefficient in the balanced equation. Okay, it just means the coefficients when you write your balanced equation. This is a sigma sign, it just means the sum of. So what we would do is take the entropy values for the products in a chemical reaction, multiply them by the coefficient in the balanced equation, because these values are per 1 mole, and perhaps you have more than 1 mole in a balanced equation. And then you would add all of the products together, and that's what would go here. And then you'd take all of the reactants, multiply them by the coefficient in the balanced equation, and add them together. And that would give you the sum of the entropies for the reactants and subtract that from the products. So here's kind of an abbreviated table over here, just for things that we need in these questions. So we want to calculate the entropy change for these two processes. So let's look at A. We'll do A together, and then I'll have you do B on your own. So first thing we do, which we should do for all problems, is write down the equation. So here's our equation. The entropy change for the reaction equals the sum of the entropy changes of the products minus the sum of the entropy changes for the reactants. So for A, we only have one product. It's gaseous water. So we would take gaseous water. So 188.71 times 1, because the coefficient here is a 1. And there's only one product, so that's what would go here. And then we'd look at our reactants. We've got liquid water. We find liquid water over here at 69.91, and there's a 1 for the coefficient here. So 1 times 188.71. Okay, now this is kilojoules, or sorry, joules per mole Kelvin. We're going to multiply it by moles. The moles cancels out. We're left with joules per Kelvin. Here's our products. We're going to subtract 1 times 69.91 joules per mole Kelvin. Again, the moles cancel out. That's our reactants. And we're going to get 118.8 kilojoules per Kelvin. So that's a positive value for our enthalpy of reaction. We're going from a liquid to a gas. We would expect the entropy to increase. So we would expect this value to be positive. We're going to do the same thing for B. It is a little bit more complicated, but look at the products first. Okay, you're going to find lead chloride times 1 and hydrogen times 1, and that's the sum of your products. Okay, that's what you'd put here. You're going to subtract 2 times HCl plus 1 times PB. And see what you get for your value, and then see if that value makes sense. So I'll give you a minute, plug those numbers in. And I modeled the first question. So show your work in the second question the same way, and that way you're much more likely to get the right answer. Okay, just kind of putting stuff in the calculator or doing half the work on the paper, it's more likely you're going to make mistakes. Okay, so just be careful, show all of your work and see what you get for the enthalpy, entropy change for reaction B. Okay, so we're going to take 1 times lead chloride plus 1 times hydrogen. So this is the sum of the products. We're going to subtract 2 times HCl plus 1 times PB. So this is the sum of the reactants. Okay, notice the moles cancel out. We're going to be left with joules per Kelvin. And we get negative 171.8 joules per Kelvin. Now, we can predict whether that makes sense. Well, we're starting with 2 moles of gas here. We're ending up with 1 mole of gas here. Well, that makes sense that we would expect the entropy to go down for the reaction, and it does.